Welcome back everyone to part 2 of Tensor Basics. We just saw how to convert NumPy arrays to PyTorch tensors. Let's now see how we can create tensors from scratch completely within PyTorch. Let's get started. Okay, here we are in the same notebook we left off at in the previous lecture, and we just saw how to convert NumPy arrays into tensors. Before we continue into creating tensors from scratch, I want to quickly point out the differences between torch.tensor with a capital T versus a lowercase t. And if we create a couple of cells here, I'm going to create a variable called new array and say np array. Let's just go ahead and say 1, 2, 3. And often it's a point of confusion for beginners, the difference between torch.tensor with a lowercase t and torch.tensor with a capital T. Let's go ahead and examine the differences here. And really the difference is just the data type and what gets converted. So essentially, we already saw that here in this new array, we can check the D type of this NumPy array, and it's a 32-bit integer. So what's going to happen if we say torch.tensor off of this new array, then it's going to retain this torch.integer 32-bit. Now, if we were to say torch.tensor, note here with a capital T, the main difference is that capital T tensor is simply an alias for float tensor, which essentially is going to create things and pass them in as a float. Which means if I pass in that same array, note that it's going to report back that now, notice there's a decimal point here, and this will convert it into a floating point. So if I actually check out here, my tensor is equal to torch.tensor new array, and I say my tensor and check the D type of this, then it's a 32-bit float. So torch.tensor, it's actually the same thing as calling torch. And there's another function called float tensor, and that's actually the exact same thing. Tensor with a capital T is essentially shorthand for float tensor. If you just call .tensor for lowercase t, it will infer the data type from the original object. Now, as I mentioned, instead of actually converting NumPy arrays to PyTorch tensors, often we're going to be creating tensors from scratch. So let's go ahead and see how to initialize tensors. So often when we're working with neural networks, we want to somehow create a placeholder. So some sort of uninitialized tensor that is essentially empty, and what it's doing is it's a block of memory allocated according to the size of the tensor. And any values already sitting in the block are returned. And it looks a lot like just creating a tensor of zeros, but really the idea behind this is to create kind of a placeholder ready for information. And what we can use here is torch.empty and then the actual dimensions we want. So we can say I want an empty 2x2 tensor. And so you'll notice here we get values either extremely close to 0, such as 4.9 times 10 to the power of negative 31, so it's an extremely small number. And the reason it gets reported by this, or like this, is because of the way computers have limits on storing floating point accuracy. But really the whole idea behind this torch.empty functionality is to essentially sit there and retain a block of memory allocated to whatever size you request. You can also even do like 4x2, and here we can see just a bunch of small values. And you should essentially think of torch.empty as a placeholder. Now, if you actually wanted a tensor of actual zeros, what we can do is say torch.zeros, and then pass in whatever size you want, such as 4x3. And you note here, by default, it creates these zeros as floating point zeros. If you, for whatever reason, want them as integers, which for certain functionalities that we'll see later on, we do have to specify what actual data type it should be, we can say torch. And then integer and either 32-bit or you can even do 64-bit, etc. And there's actually a table of the different data types along with this notebook. So if you open up the notebook that goes along with this lecture, we have a little table there to inform you of what data types are available and what precision is available. For certain networks, you don't want to retain that much precision because it really bogs down training time, and sometimes certain functionalities within PyTorch just won't accept precision as far as 64-bit just because of the way the network actually works. So keep that in mind. You may be seeing this D-type argument pop up in later lectures. But the main idea so far is we have this kind of placeholder, empty, which looks like a bunch of really small values. Sometimes they appear to be huge, but you should think of this as just just holding this block in memory. If we actually want zeros, we should go with torch.zeros. Similarly, there's torch.ones. Same idea here. You simply pass in the dimensions you want. So here we have 4 by 3, and it's just a bunch of ones. Just like NumPy arrange, we also have a torch.arrange as well as a torch.linspace. So if you're familiar with NumPy, this should feel very familiar because zeros and ones also looks really similar to their NumPy analogous functions. So the other ones I want to show you are torch arrange. So if you ever want to arrange values, you can say from 0 to 18, and then maybe take them in step sizes of 2. And you can see here we have 0, 2, 4, 6, 8. And very similar to a NumPy array, we can also reshape a PyTorch tensor. So you don't have to learn that much different syntax besides the fact that you're calling torch instead of NP. So now we have this tensor here. And then we can say torch dot, and there's a linspace function as well, which just returns back linearly spaced points. So I can ask for 12 linearly spaced points from 0 to 18, and I get back those results, and I can also reshape those into whatever shape I want, such as 3 by 4. No, 3 times 4 is equal to 12 here. Okay, so this looks really similar to NumPy, which is good. That means we kind of already have an intuition of how this should work. And besides just normal NumPy arrays, you could also convert a Python list. So if you really want to save some time, you could say torch tensor, and then say 1, 2, 3, and that will convert just a normal Python list into a tensor. If for some reason you've read in some data or you created some data and you need to change the actual data type stored in there, maybe you want to change from integer to floating point or vice versa, or maybe you just want more precision, like 32-bit integer to 64-bit integer. You can change this by calling the .type method off of that tensor. So what I'm going to do here is say my tensor is equal to torch.tensor, and then pass in 1, 2, 3. So if I take a look at my tensor's data type, it reports back it has a 64-bit integer. Let's say I want to change this to be a 32-bit integer. For whatever reason, I don't need 64 floating point precision. What I can do is off of my tensor, I can say instead of dtype, type, and then what this is a method off of this tensor object where you just pass in the actual data type you want. So I can say torch dot, and I can then replace it with various data types here. So if I wanted to, I could also replace this with a float. So here I'm going to say instead of 64-bit precision, I only want 32-bit precision. And then you just take your original object and reassign it. And now if I check my tensor's data type, it's now 32-bit integer. Okay, so again, you just call .type and then pass in the data type you want. So this will allow you to convert tensors from floating points to integers or whatever you happen to need. Now, finally, what we're going to discuss are creating tensors of random numbers. Often we want to initialize a set of neurons to be some random numbers, and there's various ways of doing that. So what we're going to do is we're going to start talking about things like rand, randn, and randint. Again, this should feel very familiar given the NumPy functions that we've already gone over in the crash course section. But the main ones we're going to discuss right now are torch.rand, which returns random samples from a uniform distribution over 0 and 1. So all you need to do is pass in the size you want here. So for example, torch.rand 4 by 3. This is going to produce back a 4 by 3 tensor of random samples from a uniform distribution over 0 and 1. So what that means is essentially all numbers between 0 and 1 have the same likelihood of being picked. Now if you want a normal distribution, such as randn, this returns sample from what's known as the standard normal distribution, which means that its mean is at 0 and it has a standard deviation of 1. So I can say a 4 by 3 here, and this is randomly grabbing stuff from a standard normal distribution, again with the mean at 0 and sigma equal to 1, or standard deviation equal to 1. Then finally there's torch randint, which returns random integers from low, which is inclusive, to high exclusive, and then we'll report back a size. So if you do shift tab here, after calling this, you can get the arguments here, low, high, and size. So note how there's 3 different arguments here, which means size should be passed in as a tuple parameter. So we'll essentially say, maybe I want my low number to be 0, I want my high number to be 10, and the size I want is 5 by 5. So we run this, and now we have 5 by 5, excuse me, where we randomly chose numbers between low of 0 and high of 10. Keep in mind that the high is exclusive, so you would actually never see 10 being picked. If you did want 10 to have the possibility of being picked, you have to change that to 11. And now we should see a 10 there. And you may need to rerun this since it is random a couple times to see that 10 actually pop up. Okay, so now what we're going to do is show you how to create random number tensors that follow an input size. So often you already have a tensor of maybe zeros or ones of a certain size, and you like that size and you want to create something off of it. So what I mean by that is, let's imagine we have x equal to torch.zeros 2 by 5. So if I take a look at my x, there's my 2 by 5, and the next layer in my neural network needs to have the same dimensions as this incoming tensor, but it needs to be random numbers. And instead of having to call things like x dot and then call the shape and having to remember, okay, it's 2 by 5, what I can do is say torch dot rand underscore like, and this will produce back, given the shape of x, the rand function. However, it takes in the automatic shape parameter from that incoming tensor. And there's an analogy for each of those. So there's rand n like, and again, all it's doing is it's grabbing the shape off this incoming torch tensor that we're passing in. So there's the x, and then producing either the rand, which is the uniform distribution, rand n, standard normal, and then we can also do, as you may have guessed already, rand int underscore like. But here we have to pass in the low and high as well. So you pass in the input first, and then you say, okay, I want my low number to be 10, and then, or excuse me, low number to be 0, and high number to be 11. Run that, and then it produces back this 2 by 5. So there's likes here that associate with their originals, rand, rand_n, and rand int. And all this does is, you don't need to pass in the shape. We get the shape from the actual incoming tensor. And finally, to end this lecture, the last thing I want to discuss is actually setting the random seed. Often, when you're creating neural networks and you have layers being initialized by random values, for reproducibility, you want to make sure that every time you kind of redo that particular neural network, you're starting with the actual same random values. So you want the values to be random, but if for reproducibility, you want to actually get those same random values again. Especially if you're following along with me and I want to create some random values, I want to make sure that as you're following along, you also get the same random values. So to do this, we can actually set a seed. So what we can do here is we can say torch dot and then pass in manual underscore seed, and then you pass in some seed value. So the seed is just an arbitrary number that you choose. So it doesn't really matter what integer you choose here. And often people choose 42 because of Hitchhiker's Guide to the Galaxy. It's just a reference to that. But that's to say this number is a completely arbitrary choice. The main part that's important with this number is that you choose the same number every time if you want reproducibility. So go ahead in the same cell that I'm putting this in, type out torch.manualSeed and choose the number 42. And then let's go ahead and say torch.rand and then say 2 by 3. So when you run this, if manual seed is in the same cell, then you should get the exact same random numbers I do. Keep in mind, if I actually call .rand again and run this, I'll get back a different set of numbers each time I call torch.rand. However, if you're running this in the exact same fashion that I did with these three cells, one right after the other, notice here I have in 70, 71, and 72, you should have also gotten the same set of random numbers for each three of these cells. However, if you ever want to reset, essentially, if you keep running these, you'll keep getting back different random numbers. If you ever need to reset, all you need to do is you can delete these cells. So I'm going to remove those again and just rerun this manual seed set. And as long as they're in the same cell, and that's the easiest way to go about this, is have your seed setting in the same cell as your random torch or random tensor being created, then you'll have this exact same output each time. So as long as you keep running this, it doesn't matter how many times you run this, as long as they're in the same cell, you should get back the same random values. Okay, so that's it for creating tensors with PyTorch from scratch. Notice it looked a lot like NumPy. We had the ones, the empty, the zeros, and then those random values. Okay, thanks, and I'll see you at the next lecture.